this one. Okay, let's go ahead and look at the what we've been doing and the homework 3. Get back to homework 3 and take it from the scratch over here that we had the data. You can remember this one and other few things that I'm gonna just show you over here too. Let's see. Sometimes see some words that they use in the aggressive book, they say see marginally associate but conditionally independent is the one that we call the confounded by the epidemiologist. And what the aggressive call the partial table is the epidemiologist call the stratification. But the epidemiologists call the effect modification. We call the interaction. Statistician call the interaction. So interaction is the effect modification. So if you're given like a third variable, the hidden variable, lurking variable is like a, not a confounding variable, then it's going to be definitely like a an effect modifier. So effect modifier means it's going to create the interaction term. That's the kind of like a discussion we built up in this the homework mainly. So that's a kind of the same thing. Effect modification is the interaction. Okay. So with that, let's go back to the homework and then see what we have over here. And another thing that I want to a little bit show, because yesterday I was contemplating that the degrees of freedom of some places. I just carefully looking into, because the textbook makes some mistakes, some few mistakes. I think I wanna a little bit straighten that up too. Using number of regressive variable and number of parameters interchangeably at the two different places, but without any consistency. Okay, let me see. So if we go back to this one that I was showing yesterday, this is a major thing, the goodness of fit, log likelihood, AIC, archaic information kind of the criterion, or even the Bayesian information criterion. I added that one too. This model better than some other model, then you are trying to utilize the log likelihood function, but it's influenced by the number of model parameters. When more say, explanatory variables are added, two things going to happen. Better fitting model, but still this gonna goes up. See, likelihood function is gonna go up of likelihood. Because of that one to that penalize that one or the remedy that situation, we're gonna add that this 2p. P is here. I'm gonna use the p, not k. The number of parameters, it's nothing but see number of parameters. Okay, number of parameters. This one is not right. Number of parameters. Number of parameters. There's no such thing. Number of parameters is if you want to put this one, k plus 1. K plus 1. Where k is the number of regressive variable. P is the number of parameters, including the beta node. Okay, including beta node. So the k is the number of regressors. If it is the case, p, k plus 1. So the BIC being given by the Bayesian information criteria we didn't mention about in this class, but it's another version of that one. AIC. So it should be P, the number of parameters. Here they were adding the 2P. Here they were adding 2 times ln number of, that's a sample size times P. Here. So for that test, for the global chi-square test, test. You have look at, you are comparing your current model, the current model with the, this is a current model, this is intercept model, this one to this one, this one to this one. Then when you're going to compare, they are putting 1 over there, but the global chi-square should be distributed that in such a way that their degrees of freedom should be the difference between these two. So they're comparing with that one. This is the test. This is the hypothesis. This is what's going to happen to the model, two models. Okay. Based on that one, see, this is the chi-square intercept model. That means beta not only minus covariate model or current model. And here chi-square should be p minus 1. So this is number of parameters in the current model minus number of parameters in the intercept model. Okay, 1. This p many parameters. Okay. So the last one is the deviation. The deviance chi-square. Is there a better model than this one? That means they are looking into like another model that which gonna be that better than this one. See, few parameters estimated to obtain the more probabilities. That means unsaturated in the situation like this. See, unsaturated because that if you're gonna go ahead and look at the profiles, 2 to the power of no, this is not right. This should be not the number of parameters. There should be number of figures available. K minus 1. Number of parameters means p. 2 to the p minus 1. Okay. 2 to the p minus 1. P minus 1. P minus 1. They are using number of regressors. Okay, I'm going to clean up a little bit. 1, 2. Okay, that should be then p. P means 3 minus 1. It is same as 2 to the k. Same as 2 to the k. K means number of regressors. Now it's right. Okay. It should be 2 to the p minus 1 or 2 to the k. K means number of regressors. K always using for the regressors. P always using for the parameters. So you have a how many parameters? 1, 2, 3. 3 minus 1. Or you can simply straight go to the 2 regressor variable. 2 to the 2, which is 4. Okay, it should be like that. Yeah, not k. K means number of regressors. P means number of parameters. P means number of parameters. Yeah. Yeah, then you're going to write that the deviance chi-square statistics. So reduce minus the full one. This the likelihood, log likelihood difference you get from the reduce minus this one, because this one has a more power on that one. But when it comes to the degrees of freedom, full minus reduce. Full minus reduce. Okay. The full minus reduce where degrees of freedom, this one is nothing but p minus 1, always p minus 1. It is same as the k, p minus k for the full, p minus 1. Okay, I'm going to call the degrees of freedom for reduced one q. Q means number of parameters in the reduced model. Number of parameters in the reduced model. P means the number of parameters in the full model. And kf means the number of regressor variable in full model. Kr means number of regressor variables in a reduced model. So when you take the difference between these two, df, f means like a kf minus kr is same as p minus 1 minus q minus 1, see? P minus q, because of the minus 1 and plus 1 get cancelled out. See, this is the p minus 1. You have number of regressor variables, regressors, okay? Number of regressors, but it's coming like this way, see? It's same as this one. If you use the number of parameters minus the difference, if you take the difference between the parameters, it is same as taking the difference between the regressor variables. Okay, that one I want to bring to your notice. So, So then you can remember that our first question, that if you first one we can remember yesterday we went through this one in large scale. See, logistic regression that estimate this, and this is our model. The class statement 0 using the reference category for the diabetes, sex, and exercises. It's been already done over here. Then mainly output you saw that one. See, so then is that the first one? Yeah, first one. You have a gender and exercise. See? Two, gender and exercise. See, and diabetes being explained by that one. And see, then I'm gonna show you here something. Okay. Then this one, the part B, I'm gonna show you here. Part B means perform a deviance test. Perform means you have to describe that one too, plus you can perform that one. See, is there a better model than this one? This is what's gonna happen when you set up. I mean 1B. 1B means this one. Okay, I'm here. This is the model. See, diabetes being given by gender and exercises. I'm there. So then I built up whatever I really need. I wrote that one into that plain English, then converted into like a mathematical equation, see, and with all these option x1, x2, then I came to my profiles. Then you know that by looking at this one, you can easily say whether this is a saturated or unsaturated one. This is an unsaturated one because we have how many probabilities? 1, 2, 3, 4. But we have how many parameters? 1, 2, 3. 3 parameters not enough to describe the 4 probabilities. It says there's some kind of that shortage. So then we have to add another variable. That's a different discussion. Okay. Then I converted that into the logit. I brought that one in the like a logistic regression model with the aid of this one. And then we're gonna question: is there a better model than this one? That's why they say they do that specifically. Is this a saturated model or not? That means that in another way you are checking. You added the third model, third variable, gonna be that explaining significantly that variation in Y or not. How that can be tested. You can simply take beta 3 and then test that one. See, it's a single test too. You don't have to go to deviance. That's why comparison and contrast we're gonna do it later on. You don't need the deviance test to go test this one. This one you can test by that. When you get the printout is gonna come along with all the estimates and their p-values. By looking at the p-value, you can easily figure out whether this is gonna be significant or not. Okay, that's the one way to have it. Anyhow, that they were telling us to do the deviance. Okay, so that, as I mentioned earlier, for you to see clearly. See this one, reduce unsaturated current model, full saturated suggested model. That's the same thing. Degrees of freedom, full to reduce. Full is like a p minus 1. So it's same as the k full. The other one is q minus 1. K full, k reduced. Kp being the number of parameters in the full model, q being the number of parameters in the reduced model. And you do this way, the same thing. Okay. Then you can remember this one. Okay. Our main effects model is unsaturated because there are 3 parameters estimated to obtain 4 predicted values. However, if we estimated a model with the 4 parameters, then we would have 1 parameter for each of the possibility, and there we would have a perfect fit to the data. Before that one, they're gonna ask us to check that one. Okay, you have to run the deviance test. That description is not enough. You have to run the deviance test. See, how do you run the deviance test? You can remember that I'm on 1B here. Okay, I'm here. I really need to get the deviance. I'm gonna go to my class. See, reference this one. Then gender exercise aggregate and scale and lack of it. See, aggregate scale none option request that the deviance statistics be generated, and the lack of it option request the almost that's it. Osmo the Lemshow test. Okay. So when you run this one, when you run that one, that's step 1B. See, that's why you have to run that one without even before you're going to add the interaction term. Even before you're going to add the interaction term, you're going to run that one. Okay, let's run this one. And according to their description, different categories, I set this up. Okay, then let's put 1B. See, this one, I'm interested in this one. See, deviance and Pearson goodness of fit. See, this one, see, that P value. See, that's what they want us to do, that P value. See. So I grab that one from there, see 120 point, and especially you can look in the P value. Since P value for deviance statistics is less than this one, we reject H0 means this one, that means interaction coefficient, which is interaction coefficient, and infer that the saturated model does not fit well, unsaturated model does not fit well for data. So that means you have to go and do some kind of a remedy. That's the discussion you have to build up over there. You have to get this one and then compare. That's what they were asking.
Professor, what is the formula for the deviance statistic? Is it the log 2?
Yeah, minus. Okay, I'm gonna show you. Okay, hold on.
Yeah,
I'm gonna show you. Give me 1 second. Okay, yeah, minus log 2. You're right. It's almost. Yeah, this one. That's the ratio. Actually, this is the ratio between two logs. Logs ratio actually this one. Then we're gonna take the minus 2L and minus 2L then. Because you can put this minus to the top of this one using the log rule here, then you can get the difference between log and then get the as a ratio under one single log.
thank you.
Okay, that's the one. Okay. Good. So then here, because of that it's not gonna fit very well. That's the discussion we have to build up over there. That's why they're asking, see, perform a deviance test. What do you conclude about whether there's an interaction between sex and exercise is called for? Do we really need that one? Yes, we can call for an interaction term between this one and that. And re-estimate the logistic regression, including the interaction term. Then what we did was we included and then we ran again. Then we're gonna check whether it's consistent with what we decided in part B. Re-estimate again with the aid of, now we have another interaction term. See, here we have to say the interaction term to be added to interaction, and interaction term between what and what here, gender and exercise. Must be included to make the model saturated. That's not they're gonna ask that. Therefore, an interaction term. See, therefore, I'm gonna use the mathematical notation. Okay, therefore, that's the therefore. Therefore, an interaction term between gender and size must be introduced to make the model saturated. Yes. And if that's the case, you go ahead and then make it saturated. And then it's going to be saturated. No, we can check that one. See, then part D, then that's why part D, we were looking into part D. See, I'm sorry, part C, this D, part C. That's part. See. Now you can check that one. Now I'm going to put the see beta node, beta 1, gender, exercise, and interaction term. Now I have a see. Now again, this is my test hypothesis, testing of hypothesis. This is for the reduced one, this is for the full model. Reduce means like only the reduced model, how it looks like. The model that you saw earlier. This a full model is like the model that we have now. So when you run this one, see, you can remember that. 1B, 1C, see. I'm going to introduce even the interaction term and then run. See, then you go to the deviance table. See? No, I'm sorry, not the deviance table, this table. The model fit statistics table and -2 log, see, 31, 34, 96, 31, 34, 96, 31, 34, 96 from the full model. Reduced model you got earlier when you were running that one. Can you remember? See? So not here, here in 2B. 1B, that you got that one from 1B. That's the reduced model. That's the unsaturated model. See? 31, 36, 17. 31, 36, 17. Get this one, then you're looking for this one, you went to here, full model, number of parameters or number of regressive variable, either way fine. If you go to proper parameters, 1, 2, 3, 4. The previous one, 3, 1, or with the regressive variable, here 3, earlier 2, 2 minus 3 minus 2 is 1, or 4 minus 3 is 1, either way is fine. So you can get that degrees of freedom, either P minus Q. P is how much? 4 minus 3, or K full and this one, okay, the both ways. That's the one like the probably P minus Q. So you're looking for the P value, you can get the P value. Once you get the P value correspond to that one. See, we get the P value. Here is 0. Then, and instead of that one, see, AIC, if you want, you can use the AIC, okay, as a chi-square. AIC, reduce AIC, that one will be far better, it's better. Rather than go to the -2 ln. Can you remember we had that issue? See, instead of this one, we prefer to use this one since it's a difference. I don't think it's going to be like a big difference going to emerge. See, this is a 120, this is a 118, suppose. I did this one through this route. I this one through with the aid of the Akaiki information criteria. Akaiki was a Japanese that top statistician. Okay, this one right there. So the rest I did that one yesterday. I think the comparison I did. Okay, which comparison we did? You know that how to get the OR for diagnosis to refresh your memory that we can say that. Missing one page. Missing one page. The first page. This one, okay, good. This one, no. So see, do did I use the C1 and C2 for that? The model has been written. No, not this one. Sorry, not this one. That's not. It doesn't have a. It has this one. It's clean because it's that one clean. X1, X2, X3. Oh, here. Sorry, we have calculated here. That profile. The begin 1D. That's the 1D. Yeah, this is how we get the profiles. So with this one that you can even include this one too. See, because we were not looking for that profiles. How many profiles we can generate here? That's the question. How many profiles we can generate here? See? This one, gender, and this one, gender and exercise. Look at the way that this has been built up now. Looks like we have 4 profiles. Earlier also we had 4 profiles. See, earlier 4 profiles, 4 parameters, 3 parameters. Now 4 profiles, 4 parameters. So what happened to this one? See, this variable, how come it comes into the picture over here? Can we include that one here and say that the gender, exercise, gender and exercise, gender and exercise. See, if this is 0, this is 0, gender and exercise 0. And the male 1 0, then it will be taken care of because it has been written in terms of this one. See, this has been written in terms of these two rather than including a new variable. If you have a new variable with the 3 options, that's a different story. But this will be taken care of by these two. Every time when you put the 0 0, this becomes 0. So you have to go and look into the formula and see what happened to the formula. That's it. You can remember that formula. That's the formula I gave in the very beginning. Okay, very beginning. This is the formula. Okay. That's the formula. This is the formula we tackled. So this time in a similar fashion, instead of beta naught, beta 1, x1, beta 2, x2, plus you have a beta 3, x3. Beta 3, x3. Okay. So x3, if you include here, let's say that this is x1, this is x2, x3. X3, does he have any like external options, or that it's intrinsic? Intrinsic means that it's been written based on this one, based on that one. So let's say that put 0 0. If you put the 0 0 here, formula should be, I'm going to write the formula for you to see clearly. 1 over, it should be 1 over t, should be 1 over 1 plus e to the minus beta naught plus beta 1 x1 plus beta 2 x2 beta 3 x3. I'm talking about here. 1 over e to the minus beta naught plus beta 1 x1 plus beta 2 x2 beta 3 x3. So if it has been written, then we're gonna get the 1 plus e to the minus beta naught. They both 0. This 0, this 0, this one also 0. That time, if you want, you can put the x3 here. This one x1, x1, because they were not looking for that one. See, x1, x2. Okay. I call them x1 and x2. If you want, you can put the x3 here. X3 here, thinking that you have a 8 profiles because of 3 variables. Okay, so 0 0 0 0, and this becomes 0. Then this become like that. 0 1. See, then if you 0 1, this become what? 1. Okay. 1 no. So I'm sorry, 0. This one is still 0. 1 1 1 0. Still 0. 1 1 1. Now what? What are the other options for these two? There are no other option. You get stuck here. You cannot go further. Even though that looks like that this one look like a variable. See? then if this can become 1 only if that these two are 1 1 only. That's the only option. So you have here 0 0 0 0 1. No other than that one. So that's why it's been written in terms of that one. Then you're gonna stop at the 4. But that's enough for you to say this one is a saturated, because we have, let us see, 1 2 3 4 and 4 estimators. 4 estimators, 4 probabilities. Earlier 3 probabilities, parameters, 4 we had. That has been remedied. So if you those are the only options you can put here. Either 1 or 0, 1 or 0. This become what? Either 0 or 1. This one also either becomes 0 and 1. 0 and 1. 0 and 1. But you cannot say for a given 0, these words separately, you cannot talk about that, because it is a function of these two. It's a function of these two. Because of that, this relies on this one. Not, it cannot independently or arbitrarily assign the number. Independently, you cannot assign the number. Its number is determined by whatever the number you're going to give to gender x1 and x2. Based on that one, this will be decided. 0, 0, 1. This will be 0 again. 1, 0, again 0, 1, 1, 1. Like that. So that based on that one, whether the ones you have, this one, the saturated model, rather than another model, is saturated now. Then they're going to talk in about the odds ratios, various odds ratios. See, indeed. See, between this to that, 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 we go through one of them. They see, I wrote this one, see, x1 1, x2 1, and x1 to x2. See, that ratio, exercises, female exercise, this one, based on that one, you're going to write with the aid of these profiles. See? So this OR is what? If you're going to write in the profiles, it should be female exercises. Yes. 2 female non-exercises. D over C. That's what they were looking for. D over C. See? Odds ratio. So D over C. D over C. So then we came up with this one, because these estimates are already we have taken by running this one, running that one. Okay. So all the results are here. So this one, not this one. I'm talking about here. Says COD should be no. Yes, D. I don't see the D. 1D. In the C. They were telling us to do in C. C, okay. Because C is related to C, okay. Using the model of 1C from this one, okay, from this one, yeah. So D, you don't have to run again, it's already over there. So here all the estimates, see, so the beta values. See, you have a beta naught, beta 1, beta 2, beta 3, everything's over here. You can plug in those values based on this one. That's all we're gonna do. So we talk about that one large scale yesterday. See, so this one, see, the late one, see, D to B, D to A. See, we talk about that one. Yeah. And all the 6 ORs are developed, and then we put everything into one. See, into one. So that if you go ahead over here, see, over here, can we see all these? It's called the results. What's ratios? See? This one, see, deviance. No, no, no. Then How could we gonna get that one? We can get that one by ask them to show, no, what's ratio, see? Show the odds ratio. See? See? Let's say that see, can tell them to show that. Odds ratio. You can ask them to show this one. See? See what's ratio, gender, exercise. If you want to add that one, the gender between exercise 0 and 1. What is the other one? The female to male, gender female to male. I think that we cannot take everything. We can take everything, but if I run this one, let's see. Exercise no ears for female. Okay, that one. Okay, first one of containing the course. Ratio. Gender, okay. Exercise 0 and 1. Yes. Let me run this one. Let me run here separately. See what's ratio? Gender at exercise 1. Gender at exercise. See, exercise. They were doing exercise, but the male to female. Male exercises, the female exerciser to male exerciser. See, this one. See, this one. That's the same thing we have over there. See, because you have to put that the other way around. The class that comment, they don't come out like that. I'm using the descending. The odds ratio gender at exercise 1. That means like a female to male at exercise 1. So that one should be, see, female to male. What? Female to 0.775. See, did you have that one? 0.775. See, exercise have been fixed. That means exercise equals 1, female to male, 0.775 by hand. See, by hand. Then what? See, then see, gender again, exercise 0 to 1. See, let's see what we have. See, gender, but at this exercise, not doing exercise, but the gender being that whether that the person gonna get the like a diabetes odds ratio for getting diabetes, for the female to male, for that who's an exerciser, is a non-exerciser. So it's going to be 0.963. Do we have that one? 0.963. Yes. See, female to male non-exercisers. Female to male exercises. These two can be by hand, and then by this one you can easily recall. See? So that's the code. See? 0 to 1. See? Then exercise and gender. See? Pretty much everything together. Okay. See, now I'm gonna say that with respect to the gender exerciser. See, exerciser at gender 0. Exerciser at gender 0. See, 554. See, gender 0, but exercise at gender 0, 1. See, so that one should be not. I'm sorry, we not gender. We can go the other way around. Gender. See, exercises to that gender. That means we for that gender. I'm gonna change that one. That means like for a male to see exercise to not exercise. Male exercise to not exercise. Male. Sorry. Male exerciser to not non-exercise. See, this means that one. See, exercise means exerciser to non-exercise. Exercise is the like that the name of that variable. Variable has a two options, same like a gender. When we call the gender, we're gonna give the priority to the female to male. Yeah, exercise to non-exercise for male. See, 0.554. 0.554. See. Within the same male, exerciser to non-exerciser. See, exercise at gender 1, female, exerciser to non-exerciser, 0.446. 0.446. So, see, pretty much everything that we got that one. See, 1, 2, 3, 4. How about this one? Female non-exerciser to male exerciser. See? This one. Non-exerciser, but the male exerciser. You have calculated 1.737. So it's gonna be here. So you're gonna have that one whether they were doing the exercise too within the same group. You put that one, but the different group. If you flip this one the other way around, okay. So let's get another. Okay. One and 0. 1 and 0. That was. No, that's the same thing. Same thing. So we're looking for exercise because they go and take that number that is the relevant one. Okay. This one, female non-exerciser to male non-exerciser, and then what's the other one? No, this one we did. To female we did, male we did. Female within that one, exerciser non-exerciser. These two. Look for this one. Okay. Female exerciser to that. Yeah. So, look for that. How to get these two easily. That okay. These two. The female exerciser to male non-exerciser, female non-exerciser to male exerciser. We can do that one. Okay. Can do that one. Okay, we can try and see this one. They will produce the same thing. So you have to. They produce the same thing. Exercise to gender 01. That one. Yeah, you can recall that one and check for that one. Okay, check for that one and see that how that can be that these two. I want you to try that one. These two, I'm sorry, these two. This one and this one. We got this, female to female exerciser, female to non-exerciser exerciser. This other way around. Okay. These two. Check for that. So then this one, what's ratio difference? Let me run this one. It will give you pretty much gender and everything. Okay, I'm gonna run this one. Should give all the combinations at the one shot. Oh. Association, then they said this squares. Response. All that likelihood estimates, least square means, that differences you can look into odds ratio and the difference. Odds ratio and the difference. I'm gonna see the odds ratio. Where's the odds ratios?
Professor, we had odds ratio in the last table.
Last
In
table.
this, yeah,
Okay.
in the output, in the output, in the
Sorry.
results.
Okay.
Yeah,
This one?
no, the
No, the
last
previous
table
one. No.
in the same results, just the table before that graph in the results.
In the result before table.
Yeah, here, if you check in difference of gender, exercise, least square, means table, the last column is of odds ratio.
Oh yeah, I'm sorry. Yeah, that's I'm very close. I cannot see. I was
Yeah,
looking for that. Thank you. Yeah, that's yeah. This is all you can get together. That by checking into the differences, because all the differences they will take into account. See, but I want to do like this separately. Do that one, and then you can get that one too. At the same time, you can get all the at the same time. See, all 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. Yeah. So yeah, see 4.4467 430 So it's based on see all the combination 11110 11100 1100 10 exercise gender 0110. See the way that how we're gonna have a look at it, because all that differences for for the odds ratio, how to get that one for the different combinations. 6 combinations we were having, that all 6 combinations we were having over here. Gender, we're gonna compare 0.446 female to female, exerciser to non-exerciser. See, sorry, here exerciser to non-exerciser, because the one is the same for the gender. See, one. Okay, then male, the gender. See, gender this one. Sorry, the gender this one. See, this one female to male, but exerciser to exerciser, with the male to female. See, 0.775. 0.775. See, female to male, but they both are exercises. Okay, then this one, see, gender one, this one, see, 1 to 0. So, male to female, but exerciser to non-exerciser, 0.430. 1430 means 0.29. See, female to male, but exerciser to non-exerciser. If this is non-exerciser to exerciser, the other one, other way around is the other combination. So then female non-exerciser, but gender the male exerciser. See, this one, 1.738. 1.738. Then female within the female non-exercise and exercise, you can see, you can easily see that one too. female, male, non-exercises, male and male, exercise, non-exerciser to non-exerciser. So 1, 2, 3, 4, see 1, 1, 1, 1, 1, 0, 1, 1, 1. Exerciser to exerciser. This one, when this is 1, this is the this 1, 1 exerciser to exerciser. Male, female, male, female, exerciser to non-exerciser. Yeah, that's right. Okay. So we have all the combinations over here. See, that one will give that one. But here, even that by giving a certain command, if you want to get that one, it's a kind of like extension of that one. But here, by making any changes, you can get that one too here. But specifically, you have to tell that one. But here, they're going to give the whole list. Okay, here. So one, then E, you can remember that we did the E. Directly show your hand calculation for the female. Evaluate that one. We did that. Yeah, the time at the average by because it's a continuous one. You can remember what we did. And then at the 0.5 at the average of that one, and then you got this one at D, and then in a similar fashion that we got that one for the it's other way around exercise for the adding this one if by making this one gender. I'm sorry, first one is exercise has been taken the average. Now the gender has been taken average, and then to the calculation. It's better off to build up this one in that way. You never can make any mistakes because that easily you can see how to get the odds ratio based on that what we given. So the given gender, what's that odds ratio between that so for a given same gender, see, but the gender has been rather than taking that one, gender has been taken at as a certain average. A to B, see, yes or no, exercise or not. 0.497. 0.497. Will that be exist? That let's say that we can double check and see point. What do you get that earlier that when female exercise to non-female exercise, you can remember 0.44. You can remember 0.44. 0.4446 female exerciser to non-exerciser, male exerciser to non-exerciser 0.554. Look and see something here. Look at this one. They will be just see this one and this one. These two values straddle with the what? This guy 0.5. See 0.5. See? So see 0.50. Let's see this one female. See little bit below that 0.5. This one above 0.5. Then on the other hand, that when we this exercise, no, is that right? That's the one we have. Okay. So gender has been fixed. Okay, gender has been fixed. That means for a given female or male, it doesn't matter. They should be having their probabilities or odds ratios close to 0.5. If that's the same answer, we get it here 50%. See, 50%. I'm talking about 50%. See, here also that one shows the same thing, kind of a close one. Below 0.50, male like around in that neighborhood, they are like it's going to happen in that particular neighborhood of 50. That on the other hand, if you fix that's the gender to this one, okay. The other one, you fix the exercise. Whether they are doing a see exercise means like whether he's doing exercise or not, but male to female. Male to female. But they are see, exerciser to non-exerciser. Male and female. Exerciser, male and female. See? Exerciser, male and female. Or non-exerciser, male and female. Look at it should be in the middle. See 0.86, 0.9. These two values. Look at. See, see. Male to female. See 0.80. Sorry, that one is 0.5. You have been centered that one at the average. It's going to be 0.86, 86%. So this one says that if you are an exerciser or non-exerciser, what's the odds ratio between male to female? Exerciser, female to male, 0.7 or 0.8. Then non-exerciser, female to male, 0.9, 9 not almost 1. See, they were going to be like a straddle between this, the straddle with the number that we have over here. So that because those are continuous one, and then they were asking us to do that one, even though this one that the categorical, see, you can evaluate the exercise average value, then average value. So part B, part B. Yeah, we get the exercise one. Then this one we can remember we did this one too, large scale. Okay, on a logistic equation with the. Now we added that age category, and then what we did was that we were running this one. Okay, we ran this one. We ran this one. See, ML is that one. See, you can write this one. See, and the age cat. See, age category. You can remember there are 3 age categories. Now we're going to take into the account that the categorical data. This one has like a categorical data. See, age cat. See, show you hand calculation for the OR for the diagnosis diabetes with respect to gender. With respect to gender. See, we did that one too. See, we did that one. See. Real quick, we did this one. I can remember yesterday. See, all these profiles, and then see this age cat has like a 3 options. Because of that one, I utilize the Z2 and C3, keeping this one C1, and then I looking into all the options. Okay, like that. And then 2C, 2C2, 2C, this one. Then you got all the odds ratio, no? Odds ratio for 2C. No, this one we have to say show you a calculation for the OR for the diagnosis diabetes with the respect to see interpret. I'm sorry, the odds ratio that we got that one. That means like for this one you have to plug in here. Okay, the odds been given. Now you have to build up the same discussion we built up earlier. So male to female, they would really want this to be happen for male to female. Okay, I told you yesterday. Show a hand calculation for the OR diagnosis, the diabetes with the respect to sex, gender, male to male. Same thing here. Same female here. With respect to not this one. Where we had the calculation. We did that one earlier. Performance test, what is the no. OR diagnosing combination. See, that's the same thing. That's the same thing. See, sex and exercise combination with respect to these two. That's a kind of like that's the same way. You can say that the show you hand calculation OR for the sex for each regression run. Here to C to B diabetes with respect to gender. So if you go here, so how do you get this one? Male to female to male in this age category. See, this age category to this age category, same age category, female to male, and this female to this age category, female to that age category, and then male to this category. See, female to male, that same category. See, or that you can see mix up to see the other one is gender. The other one is age category. Yeah, age category and only two. Okay, see, female to male. See, you divide this by that. See, so this combination beta e to the beta c beta naught beta 2 divided by e beta naught. That means e to the power of beta naught is like a beta 2 again, female. See, that's the, is that beta 1? I'm sorry, beta 1. This should be beta 1. It should be beta 1 is what? Beta 1 for the gender. Gender should be beta 1. See, this should be beta 1, okay? Beta 1, e to the beta, not beta 1. This one, I'm talking about this one. Female, this one divided by male at the same age category, then beta 1. But if you go to this different age category, see, female to set male, but the see, this age category to this age category. See, you're gonna get between these two, this age category to this one. Then you're gonna divide this by that, okay, like that. It depends on that, what ratio that you really need to have that one, that you can list all the ratios. You can list all the ratios the same way that we did over here. We had all the ratios like that, different ratios. Like that. All those ratios. From this one, so you have to you can list all the ratios, okay? That's one you can do. Then 2C2, is that the 2C2? Then you're gonna run that one with the separately by these three. So this one, and this one, and then find the, see, then show the, see, OR for sex for each regression run, see, each regression run separately. Now you're gonna see not the age cat, even the age cat, you're gonna take only one. See, the D, see, age cat, you did the E, F, see, age cat 1, see, oh, sorry, this one, 1, 2, 3, 1, 2, 3, this 2C, 2C here, these three. Age cat 1, see, you're gonna do with the diabetes with gender, but the age cat at 1, see, diabetes at gender, age cat at 2, diabetes at gender, age cat at 3. That's this equation, see, this is the equation. This is the way how you're gonna write. This is the way how you're gonna put into the program, so that you are learning both, okay? So you're gonna put into the program like that. This is how you're gonna write first, gender and age cat 1. See, this one is a gender, you have a male and female. See, male and female. This one what? 1 and 0, see? It's 1 only, see? So based on that one, see? You can think about that, all the options, because others, if age cat is not 1, see, it should be others. Others who gonna be not belongs to this category. Everyone else that this category gonna go from 18 to 34. Then the others may be 35 all the way to 99. See, we got four options based on if you're gonna put the 0, 1, and that combination, through the combination, you can get that one. But they simply that they are asking about the female to male what? Female to male, this one, or if you get the female to male, the other category, you're gonna end up with the same thing. That's nothing but e to the beta 1, right? Because that's the first one. But how do you run on this one? See, this is how you're gonna run. See, those three. Each and every one. And then if you go to the age cat 1, see, this one, second set, the third set. So you can see and say gender 0.2431. 0.2431. See, under that one. And if you go to the second one, see, second one and third one, see, that's the same thing. I wrote that there's a second the model 2. I put the 2 over here, the beta to distinguish from these ones. And 3, same thing. E to the beta 1 third model, e to the beta 1 second model, e to the beta 1 first model. See? So what I'm trying to say that from this one, these numbers I'm talking about, this one, 2431, negative 0.0505, negative 0.0505, and the third one, negative 0.2102. These three, they're going to ask, can you remember these three? That's what they're going to ask later. See, those three separately, you did that one. Okay. See? So they may rerun to perform the, show your hand differs across that. What does this suggest about whether an interaction between a sex and age cat would be statistically significant? Those numbers 1.275. Did we get those numbers from somewhere? No. I don't think so. 1.275. No. So the only thing that they're gonna ask us, show your hand calculation for the OR for this sex regression run and interpret. We did that one. See, that's a hand calculation. By hand, we did for 3 or the 2C2. We did that one. So on the other hand, 0.957, those are they available in this observation? See, 0.810, 0.810, 0.951, 0.951, 1.275. Did we get all these answers? Yes, see. But they said not to read from that one and you can verify your answer, but you have to get this one by hand, 1.275. Do you see that one in first model? Yes. Second model, that's ratio. Here, 0.951. Do you get that one? Yes. Third one, 0.810. Did you get that one? 0.810 here. See, you got that one too. So the later on they're gonna ask us what these three. Those are done. Then part D. Part D, what they're gonna ask us to do. Rerun the regression of 2A. 2A means this guy. I'm sorry, this one. 2A, this one. Without age cat, with the age cat, okay, with the age cat rerun. What does this, okay? Oh no, this one, I'm sorry. Do the OR appear different across the 3 categories of age? See? See that one. What do you think? Sex and age, statistically different or not? Can I show you over here? You saw that one. Yes, see? See, OR appear differ across the 3 categories of age. This suggests that an interaction term between the sex and age cat would be statistically significant. They're different. The ORs are different across these 3 categories. See? If they're different. See? How they differ? Are they drastically different? I don't think so. They're drastically different. OR 810, 91. This one, see, the other one, 1 point something. See, not drastically different. See, they were equals to each other. Then what? It's gonna be that confounder, no? See? Sorry, neither confounder nor effect modifier. But these are, see, kind of like a thing. Different from each other. See, are they drastically different? Yeah, a little bit. See, they are different. See, they are different. It looks like it's an what? It's an effect modifier. Effect modifier. No, that's why we are looking for the like interaction terms. See? We really need the interaction terms, so we have to figure out that by looking at these OR for each different categories. See? Can you remember the same discussion we built up with the contingency table? Here, 3 categories we have. There we built up with the two categories. Doesn't matter. But if they're drastically different from each other, it becomes what? Definitely that interaction terms. We really need the interaction terms to that remedy this situation, because they become not a confounder. They become like an effect modifier. Effect modifier means like we don't have that homogeneity. They were not homogeneous. So the system becoming that non-homogeneous. That means the interaction term will be over there. Then if you're going to draw that to graph between what and what, diabetes and then what and what happened to that? Let's say that if you draw the graph between, let's see that each categories, the age cat trophy, and then we have a gender here, age cat. Traction term. First, we'll check that one with the deviance test. Okay, let's go to D and then I'm going to come there. Okay. So this one is explained. The rerun the regression of 2A and perform the deviance test. Is your conclusion from this test consistent with your answer to 2B3? See this one, consistent. So let's do the deviance test for 2B. So the deviance test, you can remember that deviance. See? P-value, see? The deviance test, that means coefficient interaction, whether it's going to be 0 or not. Results from, see, SAS output from 2A, you can remember that the p-value is less than 0.001. If you want, you can have a look at it again. See, 2A, this one, see? 2A and B both. See? So 2D and the 2D. Okay, I'm gonna run this one here. See, under 2D, I'm running that one again. Okay. Because I want to see the deviance. That's why I put that command. Should be somewhere. See here, see p-value for the deviance test almost 0. You're gonna get that one by see aggregate scale. None will give you that one. Okay, deviance. We mentioned that one here. Okay. The lack of it option, we're gonna go to that Hausmann-Lenshaw test. Okay. So that's p-value 0. Because of that one, you reject H0. H0 means the interaction term 0 will be rejected. That means that you infer that interaction term is significant. So yes, our conclusion from this test is consistent with our results from the 2B3. Okay. So that one. And E again, see, then age category, you're going to change that one. You see. This one, estimate full saturated model. I'm sorry, this one. Fully estimate the fully saturated model. What's a fully saturated model? Fully saturated model. And we have a here gender, see, this one only, and run at this one, these two. Then you know these two, when you have age cat and this one, and on the other hand, in the beginning, you have a sex and age cat that produce what? Unsaturated model. So that means how do you do saturation? By introducing an interaction term. No? By introducing the interaction term. Okay? Introducing the interaction term. See? Now you're going to introduce the interaction term. See? See? This one, gender, age cat, and gender and age cat. Try to get the interaction term. You don't have to go with the age cat 1, 2, 3 like that. See, those are already embedded within this one for different age groups, 18 to 34, 35 to 54, and more than 55. See? So then you can see the male to female at the age cat 1, then OR this is age cat 2, see, age cat 3. See, they ask us to show the resulting odds ratio. Do this OR looks familiar now? See, you're gonna run that one. You run that one, and then you can get the ORs, or that you can calculate OR, or you can run that one. By running that one, see, you can run that, you can see that one. Then you run. No. Stop. No. Okay, good. So when you run that one, see, so when you run this one, E, okay. Yeah, see. That interaction terms, and I really need those ratios and everything. Okay. No? Spatial sense that this is the problem, no gender. You call that one gender. Age cat 1, 2, 3 for age cat 1, 1 to 0, age cat 2 to 0. This one, we did that one separately in that particular question, 1.461. Did we see that one? 1 point. Female to male. Do we see? Ratio. I'm sorry, I'm looking at this interval. Okay. 0.810, 951, 1.275. See, 1.275, 951, 810. All these we can recall by in this command, see, hcat at 1, 2, 3 to show that one. But those were we already calculated from the previous one. See, yes, they look familiar. They are the hand calculated OR for gender for each regression model in 2C. That is, see, this model, and that model for those 3 models. You can remember we got the same answer. The same answer. We got the same answer. So this actually age cut and see. Then what? Then F. Then F. No, do this look family? Yes, F. Let's go to F. I can come back again. See, we have several models. Look at how to figure out this gonna be like the they can ask whether this gonna be and modify or not. Okay, so here, no, here is age cat an effect modifier or of the relationship between sex and diabetes? Age cat, we suspect something, no? See, we suspect something. Let's see that whether that can be that verify over here. An effect modifier age cat in this one. Okay, then you go to this one, then age cat, and then if you put the interaction term, see, interaction term, that means age cat, will that affect to this one? Then on the other hand, here, see, they ask over here, this one. Then would that be rerun this one and perform deviance test? Is your conclusion from this one is consistent with yes? Answer 2. Then we found that interaction term, no, that the age categories. Okay. Then or appears across the 3 age categories age. What does this with an interaction between sex and age cat would be statistically significant? Rerun this one and then from the deviance test, we say that statistically different because we reject H naught, no, H naught, the interaction term being 0 being rejected. That means you're going to keep the interaction term. That see, now we're going to come over and ask, but if an effects modifier of the relationship between the diabetes and explain. Okay. So this one already we found age cat. Okay, though these look familiar. Okay, but for something else here. Okay, look at this one. Look at this model, gender model, diabetes, and the gender and age cat, and then model 3, gender plus age cat plus their interaction. So we go to the intercept model. We found the same model 1 intercept. See with the sorry, not the intercept model, but the gender model. These two, for the beta naught and beta 1. 1 means like a gender that female. Okay, that's why I put the female. Then model 2, see, beta naught, beta 1, beta age cat 2, 3, 2, 3, 1, 2, 3, because they were listed as a 1. 1 has been taken as like a reference line. See? And their values. See? Then with that when you gender and age cat, then later on, see, in these 3 together, gender, age cat, and everything together, that when you have beta naught, beta 1, beta 2, beta 3, see, all these and the p values. And if you go ahead and look at there, see, adding age cat to model 1, adding age cat to model 1, how much that result is in change in beta 1 on the gender of this much. See, you can remember, see, beta 1. See. Okay, look at very carefully. Okay, what I'm trying to do over here. We know this one is like a, we know this one is an effect modifier. Why? We know, how come we know that one? We know from this one. There's an interaction term. It's an, sorry, here. Remember here, we had that discussion. Whether there's an interaction term. Yes, who can do the interaction? Interaction can be done only by the effect modifiers. It's become an effect modifier now already. This is an effect modifier. Okay. You can remember that. Yes, yes. So on the other hand, okay, it's an effect modifier. I'm trying to check that whether this, the age cat gonna be a confounder. That's the discussion built in up over here. Okay, so their change. Look at their change. Change in beta 1 has been changed from here to here by adding that one, by adding whom? Age cat to gender. So I'm going to get the difference. And from the absolute value, it's 22%. And the beta 1, see, again, see, from 053, this is not the beta 1, this should be beta 2, I'm sorry. This beta 2, 0.05.137. This one is right. It's the gap between this one. Then beta 1, the second one, say 0.553. By adding the age cat model 2. Gender 1. No, this is not right. This is the difference in, this is the difference. So this one for the age cat, this one for the gender by adding gender, this one by adding age cat, this should be 2. This should be 2, no? Not 1. Why this has been, so it has been changed. Okay, this one is more than 10%. We can say this one, but this number 0.137. Okay, that's for the gender. Gender to this one, that's right. And this one minus this one, see, that one has been changed too. So, see, this gap. Sorry. But this gap, I don't need that gap. I think this gap enough for us to make a conclusion. No, age cat. This one already have this one. The B1, beta 1 has been increased. Beta 2 also check that how much been increased. Beta 2, see, beta 2 means this one with respect to this one. With respect to that one, see, gender has been increased like this way. This one also that increased. See? So that will suggest that age cat is a confounder because it's a more than 10%. That the increase in the betas, increase in betas. So 0.4553. So this one, that gap. See? Especially this one, by adding that age cat, the second model, see, gender, it has been changed. By adding this one, how much it has been changed with respect to this one, see. But the third model is like that, this model, but they both that have like a higher values. Let me see something very quickly. Make sure that percentage is right. Percentage, okay. This one, I will check that one. Second. No. Accident. Let's see. Okay, it's okay. Okay, contingency table, this one. Yeah. Beta 1 has been in. Yeah, this one, because this one is beta 1, because it's a age cat is a beta 2 here. It's going to be compared with this one too. Okay, it's okay. See, age cat. And this one has shifted by this one, mainly this one. See, this difference in this one. See, the difference in this one. See, within the same variable, within the same variable, how much that has been changed as a percentage. Okay. Okay. So anyhow, that this one, okay, a little bit keep this one. I want to keep this one a little bit. This one is enough for you to suggest that age cat is a confounder because it has more than 10%. Add in this one to make results in a p-value beta 3 and beta 3, beta 3 2, beta 3s, that beta 3 2, beta 3 2 means like this one, beta 3 2 means this one, beta 2 means this one. Beta, there's no beta 3 in this one. Should be the beta 3 only. How come beta 3 on? Beta 3 2, I'm sorry, beta 3 2 means like this, that one for this one. Okay, I'm talking about here. Beta 3 2, beta 3 has a thing. Beta 3, see, beta 3. This one beta not beta 1, beta 2, beta. This one age cat has like a 2, no? 2 and 3. Now this both should be that beta 2. 2 and 3. This one beta 3. Beta 3. 1, 2, 3, 4, 5, 6. 6, beta 6, beta 5, beta 4, beta 2. Okay, we can say beta 2 and beta 1, beta 2, beta 2 and 3. 4, 5, 6. That's the fourth one. This is something here. It's not right. So this one beta node, this one beta 1 for different models. Okay. It's coming with the beta gender all the time. Age cat, in the beginning we don't have. In the second stage we have, the third stage we have. But this one has a 2 categories, 2 and 3 age categories with respect to that one. So those are those 2 here, okay. But worry about this labeling, okay. This one, see, these 2 for that one. Then we have what? Then we have this multiplication because of this one has 2. This should also have a 2. See, those 2 is here. See? So 1, 2, 3, 4, 5, 6. So 1, 2 here, and 2 for this guy, 2 for this guy. That's what I'm trying to say. Notation not consistent. Okay, this one is a beta naught, beta 1, and the beta 2 been for the first time that the age cat coefficient, let's look at that the age coefficient being added to this one. The first time it has two options. Okay, here two options. Here two options. So beta 2 has a 2, beta 2, 2 and beta 2 for 3, which is called the beta. Here it's not right, that one. But the numbers are okay, see, beta 2. Then later on, because of that, you have other two options too. See, as I say, adding generator to the main model 2 results in a p-value. See, p-value. See, look at the p-value. P-values, there are p-values which indicate that beta 3 is statistically significant. We know that one is statistically significant already. See, because of that, we can say that it's an effect modifier. See, it's an effect modifier. We know that one. This is an effect modifier. We don't have to go in this route. Okay, we know effect modifier because there's an interaction. So the interaction between this one, see. So because of the interaction term, age cat come to the picture, and then we already put an as a like effect modifier. We modified. See, we can verify that one by going in this route. See, gender and age cat. See that this one is less than, means like a beta 3 terms. Okay, related to this guy. 3 can be kept, that one. We have already checked that one. If you can keep that one, it's going to be, there's an interaction. Interaction means effect modifier. On top on that one, we already found this going to be a confounder too. So then put together in both confounder and effect modifier in this model is the most appropriate model because of that. It's going to act as like a both. Okay, this guy acts like a both age cat. Okay. That's how we're going to check that one. But here, I'll look in this on this notation. I think it's not clear. And I was writing fast, I think sometimes. I don't see that one. Okay. But anyhow, that they both, it's going to be modifier and then as well as that the confounder. So what I'm going to do, I'm going to stop over here, and then the rest. Okay. Rest I'm going to start from here and then do that Friday, okay, because that I little not feel good, okay, but you can at the same time work on that one. This is not hard. I mean, like it takes take your time, and then this one, even that I think this one, I think we have the code over here. See, for the Q3 again, question 3. Sorry, I'm going to show you real quick. Okay. Question 3, see. Question 3, we have to go back to the contingency table. See, go back to the contingency table by changing this one and then fill this one the way that we had earlier. See, then fill this out and then the see, amend your homework to result section in this one, and this one again that you're going to compare to the see with the full model now. Investigate whether the control variables are true confounding variable with respect to the exposure. That kind of a discussion we built up. In order to do that one, you really need to build this up. But here that you're going to do the changes. What I did was that I got this one from here, and then see, I need all the see, elementary, everything like that. Then number 5, see, you can see full model, all full model. See, before that one, you do these changes. If you have done that one in the very beginning, that's okay too. See, starting Q3. Then once you have this one, you can run that one question number. This one after that one, which number we have? 3 and 3 you can run. No, awesome. This is the one that we did. That one they don't ask us to run anything over here. No? That one you can use the tables. Sorry, you have to run that one, and then you after this one you find the table. I mainly focus on that this number 5. But when you with the tables, frequency tables, you can contingency table, that command you can after this one. After this one, see here, see, I have that one over here. See, so this one here up to here, I changed that one. I got that one from the TMP2. I put it into 10th one. but pretty much everything that we need, all the variables inside that one, then ran to the tables. Okay, and with the aid of these tables, you can fill this out. Okay, you can fill this out. That's pretty much the same thing. And then there is number 5. You're gonna run the full model. You're gonna run the full model. That's the one that we are running over here. And then we can keep going. Okay, and then we can even gonna move on to that this progress check, that one to discuss with you guys. Okay.
Sounds good, Professor. We continue on Friday.
Friday in a large scale. Let's take 2-3 hours and finish everything. Okay, then you guys in a good shape. This is the last homework actually. Okay.
Right.
Okay. You guys are happy, huh? Last homework.
Yeah. Well, you know what? It's my busy time at work too. So life is just busy in general. So I'm
That's why
used
I'm
to
helping you out. I understand. That's why I'm helping you out. Okay.
Honestly, with
Go
the
ahead.
extra days, it helps out so much, Professor. So thank you very much. Because like I said, work is really busy, and like I finish like 10 hours of work, and then I'm back at school. So it's not easy. So thank you.
That's the same problem on my side to see. Every day I go to sleep like 3 o'clock, 4 o'clock in the morning. Now I cannot go anymore. I feel like I'm on that iceberg of that becoming sick.
Right. Well, we'll let you get your rest tonight.
Okay.
Can I ask you one real quick thing on deviance? Can I show you my screen too?
Yeah, fine. Go ahead. Show that one. Yeah, please. I'm gonna get rid of my one. I'm gonna stop share.
All right. And for I have my SAS open. For the deviance statistic, when we calculate between the unsaturated and the saturated model, so I believe this is the first model here. Actually, let me go back and make sure. I want to get it right. Okay, so I have my unsaturated and then saturated results. I'm not going to see a deviance statistic calculated in SAS, right? Between the two models.
You see that one. That's where is that one? You have to get that one. You have to give the command. You have to give the aggregate scale none command. / after the model, go to the model. Yeah, you have that one. See? Okay.
Right.
So.
But when I do the when I take the covariance from here, and then from the saturated model,
okay,
I get 277, but I'm not going to see that amount like here, right?
You shouldn't. That's the same thing. No, can I remember that? Hold on. Okay, that's it.
It's
the difference between a saturated model and unsaturated. Do you have both on the same place, or that? Okay, this is the -2 ln L is what? This is saturated or unsaturated? This one.
This one is saturated.
Okay, then where's the other one? Where's the other model?
The other model is.
Can you go to the code? I wanna go to. You better go to the code. I wanna see something. Which one you are running right now?
So that was the
exercise and 6. Okay.
Right. This was the saturated one. So we run this one, and then.
Oh no. There's an issue over here because that you don't put that everything. This one has a 2 variable or 3 variable. What is this one? Why you have another one here? BMI forecast exercise. Okay, then we are missing something. So where are the others? Where's the other one? That all three go together. You are missing one term. BMI forecast to exercise to that one plus 3 of them go together. Can you remember? I showed that one yesterday under this one. I showed that one yesterday. Progress check. You were talking about the progress check, I think. That progress
This is extra credit homework 2.
homework to extra credit, homework to extra credit. No, this should be. Is that the homework 2 or homework 3 you talking about?
Yeah, homework 2 extra credit. Correct me if I'm wrong, Aditi.
Homework 2 extra credit. Let me double check. Okay.
Yeah, where we want to calculate the deviance for the model without any interaction term.
And with and without. Okay.
So
But you are missing another one. No, where's the other one? Last third one. Third one. They three of them go together.
so if he adds that all the variables as an interaction term, then I guess deviance for saturated model will be 0.
Deviance of the saturated model will be 0. You add that one too.
Because that will be fully saturated model,
Yeah.
right?
Okay. Yeah.
Yeah.
Yeah. That's fully saturated. Yeah.
So yeah, Stefan, let me ping you the term for to get the fully saturated model. I have it here in my SAS.
I see.
Yeah, but even after adding that last term, it is giving deviance at 0. And in SAS we're not getting deviance as 277.75, which is the deviance value that we have calculated using the formula. So
Oh,
we're not getting the exact value that we
no, you
calculated.
don't get it because the thing is they were being rounded and then decimals being taken into account and like that. I think it should be a little bit off. Let me see what happened.
But then this is different now.
That's different a little bit than maybe. Okay, I'm gonna pull out that question first. While you guys are doing that one, I wanna see.
Oops.
Okay, let me see. I'm gonna go over here. New. And Simons. You talking about homework too, no? I show you a hand calculation. Okay. Return into a basic logistic model for table 3 diabetes. Return the model using class exercise 0, BMI for cat exercise. No, that look at that one. So why you put the interaction term? That's are they allowing you to put the interaction terms to see? Show you a hand calculation for the deviance statistics for this model. Show the relevant SAS output tables you need for this calculation. Interpret your calculated value. So when you have that one, look at the model has been given, no? Extra credit one, I'm talking about. Why you put the interaction terms? Take that out, interaction terms, take that out. All the interaction terms take out. No, just keep the same way that it's been given on that your extra credit one.
But then, okay, so like that, then I
Yeah.
remove this
You
one.
see, in the extra credit, all the code has been given. You run that one. You run that one. Why you added some extra one? Because we're gonna check that one. I did exactly the same thing today. Okay, so let's go back to the once you've done that one, let's have a look at it. That's the same thing we did in the question number 1, actually. Number 1. See? Okay. Then look at the deviance. Can you check the deviance over there? See, deviance you can see, né? Deviance, see, to go up. I saw the deviance.
Six.
See, you see, over there, see. It's p-value.
Right.
No, it's p-value. Okay, go back to over there. Then what they're gonna ask you to go over there? See? See? You are rejecting what? Which one you are rejecting now? Why when you run that deviance, that when you have a two variables, can you remember same thing that we did today? When you have a two variables, in the first question, we're gonna ask that whether you have any interaction term or not. So later on, see, this was show that the MLE for the fully saturated model, show the deviance output table for the full saturated model, just estimate the deviance statistics. Makes sense. So that you have a three of them, three variables here, BMI, CAT, exercise, and sex. Then those three, without putting that one, you still get the deviance. This deviance says what? Its p-value is 0. What are you going to reject that one? That means this model is what? Saturated or unsaturated? You can look into that one. See, the p-value is, see, rejected that one.
Right.
Yeah, then
And
show your hand calculation for the deviance statistics for this one now. Can you get this one? Can you get this one by hand calculation? Yes. How? You go to the minus, 296, that one. See, get the difference between those two, no?
it's the intercept and covariate, right?
Yeah, okay.
And then for the great. And then for and for the unsaturated model, we have 296,322. Yeah, this is what we got. But yeah, we don't see this value in SAS, correct? We're not going to see, we can't.
No,
we
no,
can
no.
only
Go back to your code. I want to see in the code again. So okay, so the which one is the one that you highlighted. Okay, for that one, what's the value for that one? BMI for cat, exercise 6, that one.
The value for that one is the 296,322.
This one. Okay, what's the other one? That's the other one.
It was the 296,044.
Okay, okay, go back to the code again.
Sorry, I'm grabbing my
No. When you run that one, your deviance, the deviance is 26 something. I'm gonna go back to that one. I saw that 26 something with the p-value.
Sorry, I was grabbing my
No, that's okay.
my charger. So if we go back, yes, the deviance for the saturated model, 26.
No, unsaturated model is 26.
No, for unsaturated, it's 303. This is the saturated one.
This is
With
saturated.
interaction terms and all.
Okay.
Yeah.
He ran this one. No, okay.
Yeah.
Okay, deviance. Okay, this is deviance. Okay, that deviance coming from what? Now, how do you get this deviance? How do you get the 26 one? Where the 26 coming from? How do you get that one? See, it should be consistent here. That 26 coming from where?
So this is the model using interaction terms, exercise, and what are the interaction terms here, Stephen?
So BMI, forecat, exercise, sex, and then BMI, forecat times exercise BMI forecast times sex, exercise times sex.
Okay, that one. Okay, this one minus that one. Why they don't give that 277 value? See what happened.
So the deviance values actually are not showing as 277, but when I checked, when I got the deviance value from unsaturated model, it's 303 something. And then when I subtracted deviance value from saturated model, which is 26 something, it's giving me the exact value of 277.75, which is the calculated deviance using that 2-log formula.
Do log formula. That means like
Yeah.
you are talking about the way that he has written over here, this the saturated one minus unsaturated one.
Yeah. So when
Okay.
we,
Which
yeah, we
one
are
gonna give you the 26? Which one give you the 26? Well,
saturated one, the one he has highlighted, it's giving us 26.
okay,
Right.
That,
okay.
yeah. And the above that, from line 135 to 138,
36,
it's,
okay.
yeah, that's giving us 303.
303. Okay, that gap is what? That gap is 26.
That, yeah, the difference of the two deviance is 277, and it is matching with the value that we have calculated using those minus 2 log 2L values.
L values, yeah, that one. That the then okay, then but it's not gonna show over here. That's why he's asking me, no, why you not gonna
Yeah,
show?
that's what our question is, that we are not like we are not getting the exact same value from SAS as deviance, but when we get the difference of two deviance, like deviance from the two
Oh, okay,
models, we
okay.
are getting the value which is exactly equal to calculated value.
Okay, I'm gonna tell you, okay, I think who is over there, Jonathan or Jonathan? Is that Jonathan?
Or it's Stefan.
Stefan.
Stefan. Stefan, what you gonna do? Can you go back to there? Okay, run this one. Is it okay? Go to code. Go to the code. I want you to do something like this. Go to the code. Take out one variable. Okay, take out one variable. Okay. Keep like that. Okay. Now run that one. Okay. Let's go with the two variables and see what's gonna happen. Okay. Now look at that. Your deviance is 70. Okay. Deviance is 70. Okay. Go to the log values and see the log value. See how much you have. 20, yeah, 29 to 90, 29. Okay, that much. Okay, 29 to that much. But this one is 70. Now you go ahead and go to the code again. Okay, then put that take out that whatever the variable you took it out, that do the interaction only between two of them, BMI for cat and exercise only. Take the rest out. Take that agenda out. Yeah. Okay. Now now run that one and see the deviance. Okay. See, the interaction term has been included. See, okay, then 29, 6, this one, from this one, can you subtract the other one, the one that earlier you had?
Yeah.
It's almost the same, no? I think almost zero. No?
No.
No? How much is that?
70, 65 negative.
That was
Hmm.
that was the deviance of unsaturated
Better
model
to,
in this case.
yeah, then that's what we did, no? Can you remember that we subtracted the log from the unsaturated, sorry, saturated and unsaturated, that difference
Yeah.
should show as like a deviance in that second model. That's what I'm saying.
Yeah, so it is giving exact same value as calculated value for two variables when we have only two variables for our model, but when it is three, we're getting different values. So yeah, that's what our question is. We are not getting the same value. So is it correct, or is there anything wrong that we are doing? Or
Oh,
I
hold
just
on.
checked that the difference is exact same value as we calculated.
Calculated, but it's not going to show on that one. For the reason is that because there are three terms going to go over there. That's the problem. Here only like two terms. The two terms that, but here even that the way that he did, I don't see that one. So can you go back to that one code? Okay, this one. Okay, for the saturated and unsaturated, use first run that unsaturated one. Only run and show me that one little bit unsaturated one. Okay, that one is deviance. Deviance is
You
so
have the 70.
yeah, it's gonna show the deviances over here because that is gonna show and say that it has to be what the p-value. Go to the p-value. When you go to the p-value, you are telling that you reject something. What do you reject? That's the question here. What do you reject here? You're gonna reject that what? The whatever you hypothesized. You hypothesized your interaction term should be zero. You reject that
Right.
and say it has to be included. It has to be included. Okay, that's what it says over here. Okay,
Right.
but that 70, what that 70, where did you get 70? Now that's the question. How did you get that 70?
It's the difference of log likelihood of unsaturated and saturated models.
That will give you 70, no? That's exactly that one, no?
Yeah,
Yes, that's what
in
we
this
got
case,
Yeah,
we are
then
getting the same value.
yeah, then
here.
you okay now. Yeah, see, okay, now you got that one. That
Right.
means look at the interesting thing. Even before you're gonna go for that interaction term, ahead of the time, they're gonna give you the that heads up and say, hey, you when you take the different that saturated model, if you go to the log and subtract the log in unsaturated one, that would be the same as that one that is gonna appear over there. See, it should be same thing for that. Okay, let's go to that now. That then now is saturated and unsaturated difference will be displayed ahead of the time. Is that right? The deviances that the log difference between the saturated and the unsaturated one will be displayed as a deviance on the unsaturated one. Okay. So that
Yeah.
yeah, that we see that let's say that you run the second one. Okay, second one run and you get the log value. When you run that one, okay, run that one, okay, run and go ahead and see. Now what are you going to see on the deviance on that one? What do you see the deviance? Zero.
0.
Zero, because the interaction has been included and you cannot go further from that one. That means they're going to just cut off everything because earlier you got that one. Now let's do the same thing for the three variables and see what's going to happen. Okay, let's add the three variables. Okay, so X,
And exercise times sex, right?
Yeah.
Okay.
And do we also need to add those three BMI
three,
times exercise times
Mhm.
6?
Oops.
Okay, now run the unsaturated one with the three of them. Yeah. Okay, that value, where's the deviance value? 303, 33. Okay, keep your, then get that one value. Yeah, 296 on to keep it.
Okay. And we run this one.
Okay. It's okay.
In the last one, yeah, BMI focus.
Okay, so let me put these in.
Okay, then you okay, go to the okay, you put that one too. I want to see the deviance too. Check the deviance. How much the deviance over there?
Oops. Deviance was 0
Okay,
now.
okay, that's good. Okay, good. Okay, get that one minus that one. Yeah, that's the same
There
thing.
we go.
There you go. It came ahead of the time. That's what I'm telling. Whatever the deviance that you are supposed to get after that difference, you're gonna get ahead of the time. That's what I showed today too. In a test, look at the 1B in that test 3. Sorry, if I go back to 1B, sorry, 1B, yeah, is there any better model than this one specifically? Then we ran the deviance statistics. When we ran that one, what happened was that we got the deviance ahead of the time that's going to be later on between the two differences from the saturated and unsaturated one. They give the deviance ahead of the time. They say this much of the deviance you should have. But when you run that saturated one, deviance go away. It is fully saturated.
Understood.
Then now, okay, that's the same thing. Okay, I'm gonna show that one more time on my side too. Okay, my side too. Okay, so this is what I was talking about. This question we were talking about. This question. Look at. I'm talking about homework 3. See, is there a better model than this one? Means you are trying to run this one. And here we have only 2. See, there we have 3. Doesn't matter. See, and then for this one, see. From this one, see, from
Wait,
this.
sorry, Professor, we can't see.
Oh, I'm sorry. I'm sorry. I didn't share you yet. That's the problem. Okay, I'm gonna share. Okay, so look at the 1B. Okay, we're gonna say that is there any better model than this one, specifically saturated model? We have to check that one. How do you check? I'm gonna say my interaction term would be 0, but I run this one. See, that's it. It should be deviance 1. Whose deviance 1? Deviance is nothing but the difference between the reduced to full model. I don't have a full model yet. I don't have yet. I don't have. What I'm gonna do, I don't have it. I went to the, sorry, that one, I don't have it. Okay, then this one, we're gonna talk about that one. Later on, what I did was, I ran that one, without interaction term. Then I got this p-value. See? This deviance gonna give you ahead of the time. Look at this deviance gonna give you ahead of the time. It's 1B. Okay, let's go to 1B here, right here. Okay, let's run this one, 1B. Okay, 1B, 120. See, deviance now gave. They tells us something very clearly. They say that this value minus the next one, that what I'm supposed to have that suggested model, which is an interaction with the interaction term, that one should produce that kind of like a log value. The difference between that log value and this log value should be the same. Same as the deviance they suggested.
0.
Yeah, that one 0 plus, look at the 31, 34. I'm going to use a calculator and then 31, 34, 96.49 now, minus earlier one. Earlier, without that one, I ran that one. I got log likelihood 31, 31, 36, 17.06. Did I type in? I don't think that I did right. I'm gonna go back to the previous one. 1C, run this one. I didn't type right. This deviance. Sorry, the log minus 2 times log 31, 34, 96. 34, 96.49 minus. Then I'm gonna run this one. It's gonna be 31, 36, 70. 17.06. 06. Yeah, difference is 120, 57. Do I have that one here? Yes. So here, see, exactly. 120.557. That's the unsaturated one. Unsaturated one, this value gonna give you ahead of the time. If you subtract from this value, from the saturated one, the unsaturated this value, that will becomes this one. So you have to get the difference. It's going to show you that one is already shown, already there. But make sure that you're going to run with all that interaction terms correctly. See, when you have a 2, you put 2 only. But see, I took that simply I run this one, I got the deviance. That's it. That's all deviance is from this guy only. That deviance is such that the -2 log L from this guy minus the -2 L from that guy. That difference is same as the deviance coming from the unsaturated model. So you are simply checking how much by how much it has been deviated from the how far that my model is away from that saturated model. Okay, it displayed already in the first time.
Got it. Thank you, Professor.
Okay, anytime. Okay, then see you on Friday. You have a good night, and then you both okay, and then stay safe and be well, and see you on Friday. Take care. Okay.
Yeah,
You
Bye-bye.
too.
thank you, Professor, for your time.
Thank you very much. Take care. Bye bye. Good night.